So the next video is on conservative versus non-conservative forces and the work mechanical energy theorem, and this is covered in chapters 9.5 and 9.6 of the textbook. Okay, so what do we mean by conservative forces? So this came up in chapter 8 actually. So we defined, because in chapter 8 when we talked about potential energy, we said we defined potential energy associated with something called conservative forces, although we really didn't define it at that time. But it turns out you can only define potential energy for things where it only depends on the position of the objects. So potential energy only depends on position, initial position, and final position. And in order for that to be true, then the sort of forces you can define potential energies for must be independent of the path that you take. Or another corollary to this is to say that if you look at work and you calculate work around a closed path, so you come back to the point you started at, so for one of these conservative forces, the work done there is going to be zero. Okay, so conservative forces are things like gravity, the elastic force, so things that obey Hooke's law, and the electromagnetic force, right? So if you think of gravity, so imagine you have an object and you lift an object, right? So there's some amount of work done, so by gravity, when your object moves from here to here. Now you could also think, now what if my initial and final points are exactly the same, but I take a different path? So instead of going straight from point A to point B, I start at point A, I go over, I go up, and then I go over, and I end up at the same point. Well, for gravity, the work done is going to be exactly the same, because the side-to-side part, there's no work done, right? So gravity is down, the displacement is perpendicular to that, so there isn't going to be any work done. So gravity is a conservative force. So non-conservative forces are things like friction and air resistance and drag forces, or like applied forces, right? So you have a person that's pushing on something. Those are non-conservative forces, and you can't define a potential energy associated with it. So then we can now talk about the work mechanical energy theorem, because if you don't have any non-conservative forces, so if you don't have friction or air resistance or anything like that, so the work done by an external force can either change a system's kinetic or its potential energy. Well, kinetic and potential energy we know is mechanical energy. So another way to look at this is to say that the total work done on the system must equal the change in the mechanical energy of the system. So to write that as an equation, so this is the work mechanical energy theorem. Sorry, that should be work mechanical energy theorem. So the total work done on the system is equal to the total change in mechanical energy, or since mechanical energy is simply K plus potential plus kinetic, we can write it as total work done is change in kinetic energy of your system plus change in potential energy of the system.